Let's take a look at a adjustment example. A leveling example that's right here, level.m. And we've got several leveling measurements. And it looks something like this. So this is HA. It's a benchmark. HB. HA is a given benchmark. HB, HC, and HD have to be determined from the measurements. This is measurement number 1. And it's going this way. This one is going this way. This is measurement number 2, H2, little h2. This is H3. H4 and H5. So this is increasing this way, and this is increasing this way. So given HA, H1, 2, 3, 4, and 5, and from this we have to determine HB, HC, and HD. So that means we're given 5 measurements and 3 unknowns. So it's an overdetermined system, and we have 2 redundancies. So we have to write down the measured as a function of the unknown. So let's write down H1, H2, H3, H4, and H5. As functions of our unknown values. So again, this is the tricky step. After this, it's going to be all the same. It's just writing down the equations that's difficult at first, because we're not writing down the unknown as a function of the measured, which would be the standard procedure, I guess, but we're writing down the measured as a function of the unknown. So H1 is HB minus HA. H2 is HC minus HA. H3 is HB minus HC. H4 is HD minus HB, and H5 is HD minus HC. So now we have to rearrange this so that the knowns are on one side and the unknowns are on the other side. So HA is a known, so that has to go on the one side. So for the first equation, it's going to be HA plus H1 is equal to HB. HA plus H2 is equal to HC. And this is already given. HB and HC are both unknowns. HD and HC are both unknown, so this is good. Well, let's write that down. So these are the rearranged equations. H4 HB, that's a B right there. And H5 equals minus HC. It doesn't matter what order they're in, as long as it's consistent. So let's take a look at the first equation. And in our example, this is going to be our first equation. So the partial with respect. So now we have rearranged them so the knowns are on one side. This is my known, and on this side we have our unknown. And it doesn't matter what order they're in, as long as the order is consistent. So in the example, this is going to be the first equation. The partial with respect to C, HC. The Jacobian is the partial with respect to the unknowns. So that's 0, 1, 0. And this is going to be our second equation, 1, 0, 0. This is our third equation, HB, HC, 0. This is going to be our fourth equation, HD minus HC, and HD minus HB. So the order is going to be slightly mixed in this one, but that doesn't matter as long as the measurements are, as long as the order is consistent. So now let's calculate our vector of the knowns. It's going to be in the same order as this one. So H2 plus HA. H2 plus HA is 6.1. So that's going to be our first, well, this is our first equation. This is our second equation. This is our third equation. this is our fourth equation. And this is our fifth equation in the example. Again, the order doesn't matter as long as it's consistent. So for the second equation, h1 plus ha, 1.9 plus 5 is 6.9. h3 is just 1. For the fourth equation is h5, which is 1.8, and h4, which is 0.9. Plugging back into our generic solution, A transpose A inverse A transpose Y. And for the x vector, x is a vector of the unknown in this order. So x1 is hb, hc, and hd. Calculate the residual and the sums of the squares of the residuals. So I'll just download this. Let's run it. And there are our adjusted values for HB, HC, and HD. There are the residuals, the sums of the squares of the residuals. And let's calculate our adjustment check from a previous example. I'll just copy it. Paste it in here. Our adjustment check is a small number, residual is a small number, the sums of the squares of the residuals are small. So it looks like it worked fine. Again, if you don't like the P inverse, you can use the exponent minus 1. And we get basically the same values. Or the inverse command should work in this case. Again, the difference between the P inverse and the inverse is the P inverse can be used if there's a great difference in the values of the Jacobian matrix.